Hello. In this video, we're going to explain a little bit about what are these affordances. So that is this fourth layer, just above the hardware in the AIOS that we have developed. So affordances are basically they define what action is possible in any given moment in terms of tools that the agent can access to complete the task. That's what is possible, what it can do. Of course, the agent as an LLM can use its own reasoning and thinking, but they usually prefer to call a deterministic tool because it will reliably give a better answer. So this is basically allows the software and the agent running to interact with hardware. This is resources, functions, without becoming unstable. And we're going to look at two examples. They're very, very different examples, but they're both affordances. So one of them is the hardware abstraction layer, which basically allows the agent to send a command to the hardware in order to change something in the physical device, which may be to start or stop growing a certain semiconductor thin film layer, for example. And then the AI workbook, which is more of a discrete tool to solve a subtask of the process, usually a complicated task that would take human hours to solve. We use these workbooks to solve them in a much shorter period of time. And we have seen an even five-fold decrease in the amount of time that it takes the AI model to solve a task that the human would solve. Now, the hardware extraction layer, for example, so the first of these two affordances, what it allows is one thing is clean human readable information to be, and importantly here, it's what is useful to the user, useful to the human, to be derived from all the noisy device data. So you typically have sort of 50 devices connected to one of these systems, but you typically only want to see a handful of values at any one time. And it allows safe, reproducible, stable software hardware interaction. And that's very important because you don't want this to be something that is unreliable in production. So this is how, in the two extremes, essentially you have this hardware. So this is a typical MBE system that they have at the Paul Drude Institute, so who is our partner in this endeavor. And this is the hardware that I'm talking about. You see, they all have different little LED displays, numbers, and it's very daunting for a user to look at and understand what's going on. And what we do is we take this information and we present it to the user in a very structured way. And this is achieved through this hardware abstraction layer. And then the user can interact. So they can change values and open and close shutters, for example, which is one of the artifacts of MBE growth, in order to coordinate the system. And how it does that is so that the hardware extraction layer actually, so here we have the hardware, this is the physical device, and usually there are 50, as I said, 50 discrete devices that coordinate together to make an overall MBE system. So a molecular beam epitaxy system that grows these semiconductors. And like in Windows, where you have a device driver, so we have it's not as low level as a driver, but we have a device library, which allows Unicorn One, the software, to talk to the hardware. It explains what the internal registry of the device is, what the communication protocol is, and how to parse the messages, which are usually low-level bits traveling back and forth. The devices themselves are controlled by a port manager. So the devices are connected to serial ports. They're connected to TCP/IP ports. They might be connected to a software development kit from a vendor, which is like a software interface. And their interaction needs to be queued and scheduled because you can only have a single communication to the device at any one time. And further behind the port manager, there is a data manager, which is essentially a cache of this registry. The registry is all the values on the device. So this defines the registry, and here we cache the registry. And it's basically, we've got a copy of everything that the hardware has in terms of its internal state inside the software now. And we maintain that as rapidly as possible in order to keep it up to date. And then we have to translate that cache, which is just a load of numbers in memory, into something that's human-centric and relatable. And we can also do second-order interpretations and causality chains with that data, more advanced things. And what we do with that data is then we display it in the application, which is where the user reads the data, and they can send write requests, which trickle through the system, gets queued, and gets sent to the device. And they can visualize these second-order interpretations in terms of charts and tables and figures. And that's the hardware abstraction layer. The second one is this AI/ML workbook, which is a totally different tool. Okay, so the first one is how you communicate with the hardware, how do you schedule tasks, and how would the agent schedule those tasks. This one is how do you do a very complex subtask it actually has many steps, but it's only part of the overall process. And this is a callable tool with deterministic logic, which means the decision process is hard-coded, but it can use AI, machine learning models as resolvers when the decision is implicit, or there are many variables. And it provides a means of the user extending the Unicorn 1 core program because they can add these AI ML workbooks as plugins. They can be executed by a human, or they can be executed by a machine. So they can be scheduled and executed by the agent. And they perform, as I said, a discrete bounded task that is part of a larger flow. And in order to achieve that larger flow and make it something where the user doesn't have to intervene, this is what we need the agentic agent to be able to do in a long term, which is why we need this kernel layer in order to allow the agent to work over a long term. So we can string together these discrete tools to achieve the overall task of maybe designing and growing a semiconductor sample, where right now we can only do one. We can only do one small task in that overall task. And what we're talking about is basically AI orchestration of the entire usage of the machine. So it can be done without human intervention. So this is a workbook, and essentially this one provides, for gallium nitride, it provides a couple of functions, this workbook. It's one of the more complicated ones. It basically gets you to a point where you can understand and determine the sample temperature, which on sapphire substrates is complicated because you can't use standard pyrometry. So you can determine one, the sample temperature, and second, you can determine the growth type and optimize the growth type. And this is everything that you need to do from having a bare substrate to getting it ready to grow the device. And this is a core part of the process. And if we could then chain this with the next process, which would be to start growing the buffer layer, to grow the active layer, and to grow the terminating layers that would complete the device, now the AI agent would be able to grow a whole device itself. And that's what we're trying to get to. And this is a building block in that process. So in our software, which as you've already seen, is called Unicorn 1, the workbooks live here. And there are ones that are authored by us, our company, and there are ones that are authored by users. So these are the ones that are extensible. So if I open one of these workbooks, for example, the playback of a video, so you get
Intensity data loaded from file.
the AI agent
Street
talk
temperature
to you
equals
and explains to you what's going on.
652 degrees C.
And we can see that this is a read video up here. This is a still image of the whole video. This is basically a playback. And here is the output of this video. So we're monitoring the intensity of the square, this one here, in fact, over time. And the intensity of this changes depending on what's going on the surface. And we use this profile to basically, we need to pull out key points in this. There's an inflection point here where the intensity basically it's dropped and then it stabilizes. And there's an inflection point here where it from its trough, it starts to increase. And we use this AI/ML tool to find these points. We've trained it to find these points. And you can then, from these time indexes and some knowledge of the fluxes, which the software, this unicorn software does, the cell fluxes, we can determine the substrate temperature. And this is a very important task that the user used to have to do manually. There was no program, there was nothing. Even though this has been known for more than 25 years, there was no program that existed that did it automatically, that used existing art, literature, and encoded it into something that could basically complete the task that the human was being forced to do manually. And indeed, as I said, do it 5 times faster than the human can do. And that's what we've achieved.